This is the second part or part B of question number 239, which is in this question we have to find the moment of inertia of a cone about an axis of symmetry whose mass is m and radius of the base circle is r. So from this diagram of the cone, it is given that the radius of base circle is r and height of the cone is h. Its corresponding angle of cone equal to alpha. If we take a small disc-like segment at a distance x from the topmost point of the cone, which makes an radius r with the cone and whose thickness is dx. So from the geometry, we are seeing that x divided by r equal to tan alpha. So we can write r equal to x tan alpha. Again, area of this segment equal to pi r square, that is equal to pi x square tan square alpha, as r equal to x tan alpha. Again, volume of this segment will be v equal to area into thickness. So its area is given by pi x square tan square alpha, pi x square tan square alpha into its thickness is equal to dx. So this will become pi tan square alpha x square dx. So this is the volume. Now mass of this small segment, if mass of this small segment is dm, then we can write its mass dm will be equal to its volume into density. So as its volume equal to pi tan square alpha x square dx. This is the mass, and it's multiplied by its density rho. Now density of this cone will be rho equal to mass divided by its volume. Its volume equal to 1/3 pi capital R square h. So its density rho will become 3m divided by pi capital R square h. Now if we put, now the mass of this element dm is equal to pi rho tan square alpha into x square dx. Now moment of inertia of this annular segment di will be equal to dm into r square divided by 2. As this is just a disc-like segment, as we know the moment of inertia for a disc is equal to I of disc is equal to m r square divided by 2. So now we will substitute the value of dm and r in this equation of di. So if we substitute the values, we will get di which is equal to dm. dm means pi rho tan square alpha x square dx, and instead of r square we can write it is as x square tan square alpha divided by 2. So our di will be pi rho tan square tan to the power 4 alpha x to the power 4 dx divided by 2. Now the total moment of inertia of this cone will be the summation or integration of all these annular discs range from 0 to r. So its moment of inertia I will be integration of di. So integration of di will become pi rho tan to the power 4 alpha divided by 2, and integration of x to the power 4 dx. Now the range of x is from 0 to, and the range of this x is from 0 to h. Now we will find the total moment of inertia by putting all the values. So this will be equal to pi by 2, and value of rho is 3m divided by pi r square h, and tan to the power 4 alpha equal to, as from this figure, tan is given by r divided by r to the power 4 divided by h to the power 4. because here is given it is 10 to the power 4 alpha, and integration of x to the power 4 dx will be x to the power 5 divided by 5, and its range is from 0 to h. So our total moment of inertia I will become pi upon 2 3m divided by pi r square h into r to the power 4 divided by h to the power 4 into h to the power 5 divided by 5. Now if you cancel the terms, here is h, there is h to the power 4, so ultimately we can cancel the h to the power 5, and there is r square, there is r to the power 4, so and there is pi, and this pi will cancel each other. So its moment of inertia of the cone about the axis of symmetry will be 2 divided by equal to 3 divided by 10 m r square. So moment of inertia of a cone about its axis of symmetry will be 3 divided by 10 m r square. So this is the required or short moment of inertia for a cone about its center of symmetry or axis of symmetry.